Yes, Dinara, we have a tilted coordinate system because I don't have a real tripod right now. Okay, question 4 asks us to imagine that we're trying to push a table over a floor that has friction. So here is our table. There's some kinetic friction coefficient, which we know. And we push it a couple of different ways. So first, we're going to push it flat. Part 2, we're going to push it directed 20 degrees above the horizontal. In part C, we're going to push it at 20 degrees below the horizontal. Part D, we're going to push it at 60 degrees below the horizontal. Something funny is going to happen here. That's 60 degrees. And then part E is something I will discuss as we go, which is, without doing any math, why do B and C give you different answers? So what is the dealio here? The big idea is that the frictional force here depends on the normal force. Let's write down the sort of thinking steps. And it's always a good idea when you're doing a problem to kind of think through what's going to go on and try to anticipate not what the math will look like, but what the physics is. So we're trying to figure out how hard we have to push this thing to make it move at constant velocity. So how hard we push depends on the force of friction. Which depends on the normal force. But the normal force is not equal to the weight of the thing. Because the pushing force also has a vertical component. So what that means is, for instance, B and C are not going to be the same because in B, I'm pushing up a bit, so the normal force is going to be less than the weight of the thing. But in part C, I'm pushing down on it, and there the normal force will be greater than the weight of the thing. I mean, you might imagine that if I have a table in front of me, I want to push up or lift and pull to take some of the weight off of it and reduce friction, rather than to pull it down into the ground or push it down into the ground and create more friction as I'm trying to make it go. So this is a thing we all know intuitively, but we want to do the math here. So we're just going to go through these one by one. Now, I do give you some numbers here. This is 120 kilograms. The coefficient of kinetic friction is 1/2. These numbers do become important on part D. So, A. All right, force diagrams. What do we have? Well, normal force goes up. Gravity goes down. Should move this label. We're pushing to the right, F push, and then friction goes to the left. So we have X and Y expressions of Newton's law. So in the X direction, let's see, I've got minus mu K times the normal force plus F push equals max. And in the y direction, I've got the normal force minus mg equals may. Now, it doesn't move up or down. And in the x direction, we're just trying to make it go at a constant rate. So the accelerations are 0 in both directions. That's nice. So in the y direction, we get that the normal force equals mg. This is not always true. It's only true here because I have no other forces in the y direction. That's going to change. So then we take this, we substitute it in, and we get minus mu k times the thing we just substituted in for the normal force plus the pushing force equals 0, telling us that the pushing force is mu k mg. If that's 120 kilograms, g is 10 meters per second squared. This gives me 600 newtons. So that's part A. What we're going to do now is we're going to change these things one by one and see how our equations change. So I'm going to erase everything. We're going to move on to part B. Now, the thing that changes here, is this now goes up. I'm going to draw my diagram bigger because now I have to do some trigonometry. So again, for my table, let's see. Its weight goes down. We'll draw that in peach. Weight goes down. The pushing force now goes up at an angle. So the x component is going to be Fp cosine theta. That's theta. This is going to be Fp sine theta. Again, I have a normal force going up, and I have a frictional force going to the left. These arrows are not to scale. How could they be? I don't know how big the forces are yet. So, as before, now I have x and y equations. Newton's second law in the x direction. Let's see, I've got two forces. I've got the x component of the push and friction. So I have Fp cosine theta minus mu k Fn. Go ahead and put 0 over there because we know the thing doesn't accelerate. But now, in the y direction, I've got a new challenger has appeared. I have the normal force, but I'm also pushing up a little bit. So now, I'm going to do the same thing. I'm going to solve for the normal force, and I'm going to put it in here. But now what do I get? I get that the normal force is equal to mg minus Fp sine theta. Right? This makes sense. The weight the ground must support is whatever the thing weighs minus however hard I'm pushing upward. So now we're going to take this expression. We're going to stuff it in there. And that gives me Fp cosine theta minus mu k times the thing I just found, which is mg minus fp sine theta equals 0. So now I've got to solve for fp here. So do that by collecting all of the terms that have got fp in them and putting everything else on the other side of the equation. So what do I have? So the term that has to go over there is mu k mg. So I've got fp cosine theta. Minus times a minus is a plus, so plus mu k fp sine theta equals mu k mg. Just color coding here. fp. So now what I'm going to do is I'm going to divide the left-hand side by cosine theta plus mu k sine theta. So that gives me fp equals, so the numerator is mu k mg, divided by cosine theta plus mu k sine theta. This denominator is just a pure number because trig functions and coefficients of friction are just numbers. This is a force, so my result is a force. Let me do the math. I'm going to have to use a calculator for that. So that's going to give me, where is a window where I can type this? Here's one. So mu k is a half, so I have 0.5 times mg is going to be 1200 newtons. Divided by, let's see, what do I have? I have the cosine of 20 degrees plus a half of the sine of 20 degrees. Oh, I made a typo in Google Calculator. Okay, so this gives me 540 newtons. Let's record our answers, just to make sure we understand what's going on here. So part A gave us, I had to push with 600 newtons. Part B, I had to push with 540 newtons. So for part C, we're going to be clever. We don't need to erase the whole board and start again. We can just change some signs. Because all I'm changing for part C is now, rather than pushing up, I am pushing down. I also messed up my eraser. I'll fix that later. So now, what's different? Well, this force is different. Now I'm pushing down. Again, components. This is going to be fp cosine theta. This is going to be fp sine theta. And the overall one is, of course, fp. But now, for part C, which I am working on, I'm just going to take my work from part B, and I'm going to change some signs. So in the y direction, now rather than this being up, this is now down. So that sign has changed, which means this sign now changes. So what is different is that now the normal force is bigger than the weight, because now I'm pushing the thing down into the ground rather than lifting it up. So let's now propagate this change in signs. Now when I plug in for the normal force, this minus sign becomes a plus sign, which means that this plus sign becomes a minus sign. This plus sign becomes a minus sign. And now I have to do my calculator work again. So I'm just going to change that plus sign to a minus sign, run the calculator again, and now I get 781 newtons. This makes sense, right? This is what we expected. We expected that if you push down on a table rather than pushing up on the table, here I'm increasing the normal force and making friction worse. But now, all that's changed from C to D is this has changed. The angle has changed. And something funny happens here. The funny thing that happens, it takes some interpretation. So if I just take 60 degrees and I shove it into this formula, right? If I change the 20 degrees to 60 degrees and I just hit enter on my calculator again, oh, I changed the numbers in this problem too, and this is possible. When I do this, in the numbers I had the last time I gave this problem on a practice exam years ago, this would give me, this was bigger than that. And it gives you a negative in the denominator, and you interpret that as, hey, that's not possible. You're pushing down on it so hard that you pushing down generates more friction in the y direction by increasing the normal force than it creates pushing force in the x direction. But with the numbers I gave you this year, it's possible, but just barely. You get almost 9,000 newtons. Because as you're pushing down at this steep of an angle, you're generating friction by pressing down almost as efficiently as you're pushing it to the side. Part E asks you why these two are different, and we talked about that along the way. Are there any questions about this problem before we move on from the folks who are watching? This is a very good sort of thing to understand. If you understand what's going on in this problem, then and you're able to sort of think clearly about setting up Newton's laws here and solving for the normal force rather than saying, oh, the normal force has got to be mg, then you're in good shape. So I'm going to, did I start recording here? Yes, I did.